All right, so hi everyone. Today we need to talk about organic compounds as Bronsted acids and bases. This was something that really wasn't covered all that well in the previous video. So we did see acetic acid, right, which is CH3 C double bond OOH, and looking at that proton there. And the pKa of this one was approximately 5, right? So it was weak relative to things like HCl, but it was strong relative to other compounds like ethanol. So I guess I can put ethanol down here as well. So that's CH3, CH2OH. And again, the pKa for this one is more around 16. Okay? So if we think about this H being removed as H plus or this one, what we're left with is acetate here, O minus. And again, that's after this H has been removed. And here we're left with ethoxide, CH3CH2O minus. Now you notice in both of these cases it's an O minus that's left over. So the big question is, why the big difference? This is 10 to the 11th or 11 pKa units. Well, if we look at those two anions, right, just the acetate and the ethoxide, right, those are the two important ones, okay? This is an example of resonance structures. So for this one, we can draw a resonance structure where the anion is now on the top oxygen and the double bond is to the one to the right. Here, you cannot do that. So this is an example of the resonance effect. And we saw this back in General Chem 2 for things like sulfuric acid, right? That O minus on sulfuric acid, you could draw several resonance structures, so that made it very strong. Here, the same sort of thing applies. So resonance structures mean this anion is more stable, which then in turn means the acid is stronger. Okay, so acetic acid and those kind of molecules are among the strongest of the organic compounds for acids. Again, they're weak relative to other things like HCl and H2SO4, but for organic compounds, these are among the strongest. Alcohols are kind of the next strongest, right? So those pKa's were in the 16-ish kind of a range. Most other organic compounds have pKa's that are much smaller. That is, they are much weaker even than ethanol. And I guess I'll just look at 3 of them here. I want to look at an alkane, an alkene, and an alkyne. Okay, so that's the 3 main hydrocarbons. And of course, you've got aromatics as well, but those would be represented by one similar to this. And if we look at H's on each of these, okay, pKa for this one, again, much weaker even than ethanol, is around 25. Okay, so quite a bit weaker even than ethanol. pKa on this one, we have a dramatic jump. Now this is more in the range of 40. That's even a little higher. I think it's like something like 43 or 44. So it's even, so a dramatic jump here. And if we look at something like simply ethane, pKa here is more like 50. So even much weaker than that one. So realistically, in terms of thinking about things as an acid, this is the only one here, the alkyne, that even remotely would have any acidic properties whatsoever. These two are pretty much not acids at all. And this is a case of the so-called hybridization. Effect. So this carbon, remember back to chapter 1, is sp3, it's tetrahedral. This carbon is sp2, it's trigonal plane. And this carbon is sp, it's linear. So the higher the proportion or percentage of S in the hybridization of the atom, the stronger the acid's going to be. So this one is 50% S, this one's a third S, and this one's only a quarter S. So again, this one we will see a little bit, still quite weak, but not nearly as weak as these others. And it's, it's in the ballpark at least of things like some of the alcohols and that. It's weaker than that by quite a bit, but at least it's still somewhat acidic. We can actually use it. All of the rest of the organic compounds like ketones and esters and all of those sorts of things are going to have very small pKa's as well typically. And they're going to be, well in the 20s or above. And so realistically, we don't really talk about many of those as acids. In terms of bases, right, pretty much the only thing that's going to be a base is going to be the amines. And we already know from General Chem that ammonia, right, is a base. Well, amines are simply replacing these H's with carbon groups. So not shocking that these should be bases, right? So things like methylamine, right, that's going to be a base. You can use, right, this pair of electrons on nitrogen to remove an H from something, right? So it accepts an H in the Bronsted sense. A very common one that's used quite a bit is something called triethylamine. So 3 ethyl groups bonded to N, that's used as a base quite a bit for organic reactions. Another one that gets used quite a bit is this thing called pyridine, which is actually an aromatic compound, but where one of the carbons has been replaced with an N. That gets used in reactions quite a bit too. So amines are pretty much the only organic functional group, at least of the common ones we're going to talk about, that are bases. And again, carboxylic acids are the strongest for acids, alcohols are next, then alkynes, and those 3 again are kind of the ones that we're going to be talking about realistically in terms of being acidic. All of the other ones are quite weak. One last effect, so we've talked about resonance, right? And you know there are still periodic trends, so the top to bottom and left to right from back in General Chem. I'm not going to talk about those anymore. But one last one I do want to talk about is, again, it applies to organic compounds, but to lots of other things as well. This is the acetic acid again, and this pKa was around 5. But now what happens if I replace the 3 hydrogens on the CH3 with 3 fluorines instead? What happens to the acidity of that H? Is it going to be stronger or weaker? Well, it turns out it's stronger. And the pKa for that is closer to 0. So now, right, that's quite a big jump, right? This is quite a bit stronger than that one. So TFA, this is called for any of you in biology or biochem, right? So what happened? Well, both of these, right, are going to have the resonance structures. It's going to be an O minus after this H gets removed, and after this H gets removed, right, it's going to be an O minus, right, on both of those. And they both are going to have the resonance structures. But this fluorine is way in the upper right-hand corner of the periodic table. So that's the most electronegative element. So these 3 fluorines are pulling very strongly on all of the electrons in the bonds of this molecule. So that these fluorines pulling, the fact that they're so electronegative, means that it's going to help stabilize that even more. And that's what's responsible for the difference. And this is called an inductive effect. So it's not resonance, it's not changing atoms, it's not periodic. It's the fact that these are very electronegative and are pulling strongly on all of the electrons in the bonds here to help stabilize. Okay, so there's a little bit of an intro to some organic compounds as acids and bases, Bronsted acids and bases. And again, we're going to switch then to Lewis acid and base next time and look at things where H pluses are not necessarily being transferred. Okay, we'll see you all on Friday for class.